I think it was actually a 14 that point.
4.
33.
33.
And 31. Yeah. 31 or 33. Right.
28 and then 31. All right, 28. R equals 2 theta times the square root of secant theta. And it says find drd theta. I see a product rule here. Do we all see a product? Okay, I'll go through it again.
Yeah, we did it already.
I'm going to do part 1 and part 2. So I'll do the derivative of the first times the second plus the first times derivative of the second. So I'm going to do power rule first. Remember, that's just an exponent of what? 1/2. Good job. So 1/2 secant theta to the negative 1/2. Now I need to do chain rule. What's the derivative of secant theta? Secant theta, tangent theta. And if this were anything other than theta, then I'd go ahead and do chain rule again. But since it's theta, the derivative of theta is just 1. And so I'm done there. Right. Yep. So you could leave it there if you want to go through and say this is 2 root secant theta plus, that would go away. So it looks like I have gross theta over theta secant theta tangent theta over square root of secant theta. Well, this goes down to the bottom because of the negative. So that leaves this and this up top. Yeah, sine squared plus cosine squared. Okay. That's all I see you could do with that. They went through and combined and everything. It went to the bottom because it was a negative exponent. If you see, kind of yes, but if I end up with, if I start with something like a polynomial, so 6x squared plus 7x minus 3, and I wanted the derivative here, that would be 12x plus 7. I don't do the derivative again inside here, and this is where some people were getting confused last week or right before we left. These I look at as individual pieces. If you see something where it looks like another function is embedded in another function, so maybe something like that. Since it's not just a variable, if I could take something out and replace it with u, then it's kind of embedded in there, if that makes sense.
If you have afternoon WTC and need to have your makeup picture taken, please report to the auditorium at this time.
Give me another one from your homework. These just take practice. The more.
You don't have that in your ATC. I mean.
I'll do 35 first.
I was thinking about I wasn't thinking about. I still call it.
All right, this asks us to find the second derivative.
So you just found the first one, and then you found the second. Right. That's 31. That's
Oh.
31. This one you can't make.
My mom said that.
I just have trouble writing F of U all the time. Y'all shut up. Okay. Second derivative. Nope, this is find F of G of X, the derivative. Okay. Okay, so essentially what they've done is they have identified the embedded function for you. That's what they've done.
This one is better to.
So you just plug this in here.
I did it the other way, but I feel like
Let me do it with U substitution so you see.
Like yesterday on that long trinomial, like I would have sucked at plugging in.
What's the derivative of cotangent?
Negative cosecant squared x.
And I keep the x the same, right?
Do we even memorize like every single one today? Yeah. It looks like we're done. I mean, well, we can
Okay,
derive
so
it.
if you have the first three.
I mean, I have those.
All right, so that's the derivative. That only takes care of the trig function. Now I have to do the chain rule here, right?
Yep.
So I'm going to multiply this by, what's the derivative of this?
Du.
Pi over 10
Wait, so how do you
du.
Oh, then you do du.
Yes.
Wait, so why?
Because I took the derivative with respect to u.
Wait, so you just did our rule right there, or did you do
I just did chain rule.
So
Just
then
chain
that
rule.
little thing. So then
Yes.
your d, but would your du be the power rule of u, like the
Yes, I'm going to have to come over here and say, okay, well, du
2.5.
would be, right?
Yeah. So you did a chain rule. So that pi u over 10 is the inside, right?
Yes.
But you do the power rule of that, or
No, I did. So if I asked you, what is the derivative of sine 2x? Cosine 2x, but then you do times 2, right? Because you chain ruled this. That's exactly what I did. I chain ruled this.
But you did times pi over 10 and times 2.
So I could do dx here, but in this case, x is not subbed out for anything. So the derivative of x is what? So you're essentially doing it as just always 1. In this case, my variable is not just a variable. My variable is a whole function, so I do need to consider du.
You're basically saying that times the derivative.
Yes. Yes.
Well,
When you're doing u substitution, absolutely yes.
So does that mean that du, then you can substitute that?
So now I'm going to go back and plug everything back in and just work on simplifying. So this is negative cosecant squared, and I'm going to write this way so you can see, times. Yes, you do. Because it should be 10. Sorry. My hands are getting ahead of my brain here. Now times u, remember, is 5 square root x, right? This does not go inside this. It's not a function of cosecant. It's just outside. And then I need and now it's just a matter of cleaning up.
wait, so okay, can we 5 and
Yes. If it was an FRQ, yes. I've not seen most of your trick things like this are going to come multiple
No,
choice, so
Ren,
you're
it
going to
would
have
be-
to be able to manipulate them.
Maybe 2 pi over. Tell me how you got 5 over 2. I knew it.
Maybe pi over 25.
So this is
How do we-
this
oh,
is the
it's
same
pi
thing as
over 2
5x
times
1
pi over
half.
2? Oh, we made that to it?
Yes,
No,
yeah.
I'm saying for the 5 and 10.
Oh, yeah.
Make it 5 over 2.
This would
Yeah.
be pi square root of x over 2. Right? Go ahead and put what? Yes, you could. You could go ahead and plug in one there whenever you're ready.
Like
That's fine. Yes.
Like on a shrimp. Please say on
What's that mean? A shrimp?
a shrimp.
What?
On a shrimp.
Shrimp?
Shrimp.
What does that mean?
STREMP.
Shrimp?
Let's just add it.
No,
I looked it up on it.
it's not. It's you don't know where the origin is.
You don't know it. We do it like this, like that.
No.
So yes, Katie is correct. You could plug in 1 at any point in time because it did ask us to evaluate when x equals wherever it went. When x
You gotta
equals
find
1.
the derivative first.
Well, at this point, that is the derivative. I could have put in 1 there. Oh.
No square, Miss McGee.
What? Oh.
Get away from me, man.
Where are you confused?
So you
Bang.
you multiply those with pi over 10 and 5 over 2x. Negative 1 half. You multiply that together.
Yes, so this would give me 2 in the bottom, and then 2 times 2 would be 4, and because this is negative, it's down at the bottom.
So what's down at the bottom is where
Yes, so this is really pi times 5 over 10 times 2 times the square root of x, because that's negative. Well, no, because I'm going to plug in that 1. So I've got negative cosecant squared times, and if I put in 1, then I'm at pi over 2.
At this time, juniors with the last names A through L who have not had pictures done may report to the auditorium. That is A through L, juniors only.
I guess I need to go then.
Okay, so so now this is unit circle.
Yeah, and I got it, and it's negative 1 half, but equal, this is
I
2.
hate
But
this.
2 times pi over
Squared. Squared. This is
Yes.
cosecant squared.
Yeah.
or it's
Okay, so how do you find cosecant? Cosecant is 1 over sine. So it's the flip of sine. So what's the sine at pi over 2? Where's pi over 2?
Your first quadrant.
0.
I'm up at the top at pi over 2. Right?
1.
1.
1.
Right?
It's 0, 1.
Where, think about my unit circle.
It would be 0. It would be 0.
Here I am at pi over 2, right?
Yeah.
What are the coordinates there?
0, 1.
0, 1. The sine of that is 1. The flip of 1 is 1. 1 squared is 1. But it's negative, so it's negative 1 times. Well, so it's different. If it was,
No, pretend, Van, pretend there's a negative 1 in front of this.
right. It's different, yeah.
Times pi over 4, right? We're not finished. Pi over 4 is,
Please tell me that's the answer they got. Okay.
yay. And then we can just find out what negative pi over 4 is on a unit circle.
No, Van, too much. Stop. We got an answer. We're done.
No,
We can still do
no,
that.
you couldn't. You don't have anything to look for right here. Yeah, but are you looking for a sign or true sign? Or are you looking for...
He's looking for gold.
Give me, all right, that was which one? 35?
Van's just a
And you-
waste of breath.
Yes. 31.
Y'all agree? Van is just a waste of breath too.
These are fun. All right, second derivative. These are fun.
I'm starting to. I think it's because I was going
I
through
understood the end, but I didn't understand it.
All right. First derivative should be fairly straightforward for you. What is
I don't know
that you have to remember. That's just to memorize.
Would you make an exception from
Negative
your test to
cosecant
let me
square.
have-
What? No, because you're not gonna have it on the exam. All right, what's the derivative of cotangent? Negative cosecant squared. The thought here is if you do enough of these, hopefully that it'll kind of start sticking. Good job. Then you do the inside. So this is really -3. This is where we started here. So there was no product.
Folks, there's nothing being multiplied there.
3x minus 1 is just, yeah. It's a function of cotangent. Okay. Now, yes. So now I'm into some a little bit more difficult territory. Yes. We did 35. All right, so the first thing I'm going to do is the power rule. Okay, so I'm going to work outside in. Always start as far outside as you can and work your way in as you go. Okay, so outside, remember this could also be written this way, if it helps you to see it like that. Right.
That does.
So this is -6 cosecant 3x minus 1. What's the derivative of cosecant? No, it's definitely not that. Is it secant cotangent?
That's why you're awake. Give it breath, man.
We don't have to do product rule here because it's just that coefficient out front. So we did power rule first. Now we need the derivative of cosecant. What's the derivative of cosecant? Noah, with your negative cosecant. You were right, Katie.
Right. I'm not on the intersection. Wait, so why did we have to take the derivative? Why should we just do that?
So, are we doing?
It asks us to find a second.
Are we doing product rule?
We're just doing, this is just chain rule.
So chain rule.
So this was
Alright.
power,
Now you gotta do it
Okay.
times 3x minus 1.
and then we had to find the derivative of the trig function. And now we have to do the derivative of this inside piece, which
do you
is
not multiply it by 3x minus 1 first? Or 3?
just 3. Derivative of 3x minus 1.
Okay.
Why?
You did a little bit.
We did power rule, then we did the trig, and then we did the inside.
For the trig of cosecant is
Yes, that's why it looks crazy.
No, that was wrong, man. It's negative.
Right, so this is -18, but actually I've got 2 negatives here, so I'm just going to make this positive. 18. I've got 2 cosecants, and I've got 1 cotangent. That did escalate.
Okay.
18 cosecant squared, yes.
Man, you're like a Grinch.
38.
It's like 10 minutes.
It's out East Camden
It's like out by the airport.
by the airport.
Well, that's what North Central is right now.
What'd you say, 38? F of u, u minus 1 over u plus 1 squared. Oh, gross on this one.
No, dude, I was talking to cut you off on that yesterday.
All right, let's do it. Nothing to it but to do it. Let's find the derivative of f with respect to u first. We'll find the derivative of everything, and then we will plug back in. All right. Outside in, always outside in. Power first here. So the 2 goes in front, everything stays the same. This is a power of 1 now, right? But I have to do chain rule. Times the derivative of the inside, which is the quotient. That's exactly right.
All we have to do from here is push it.
Okay. Derivative of the top is 1 times the bottom.
It'd be negative.
Derivative of u.
Oh.
I will at the end. I'll throw the du on at the end. Minus the top times derivative of the bottom.
Wait, are we doing, so what you're telling me is we're doing chain rule, but the inside we have to.
Is a quotient. That's
See,
correct.
this is just so. Yeah, that's actually pretty cool.
Oh, no one has.
Dylan, that's why you're a loser and no one looks.
But now we do need to include that du on the end because u is a function and chain rule is going to take over there. So instead of doing chain, we're just going to chain it once with the u. We're going to go in and
We're gonna
substitute.
plug that big old one in.
Well, but remember, we're evaluating at a specific point. So once we plug that big old one in, that's what gets everybody. Don't forget that.
We could simplify the fraction.
Right? Simplify a little
Can you
bit.
explain to us when and
Wait,
why
what?
we
We can't
should put that
simplify a
in?
little bit, right?
If you want to, you can, yeah.
Wait, that was just not,
No.
not that. Okay, square bar.
I'm just going to find du over here real quick.
Can you explain us in this problem why we should?
Wait, so
do this?
find du is when you plug in.
Say that one time.
How do you find du?
Du, so I took this, so it's the derivative of this one.
And then do you plug in the negative one into,
For every x.
so after you do the derivative of.
Well, we have to plug this in for every u. So I am going to clean it up just a little bit before I do start plugging that in because I'm noticing that some of these u's are kind of going to cancel out and it's going to make it a little bit easier for me whenever I plug in. Yeah, Ben. Yeah.
Nobody knows when and where to put it.
Okay, so anytime you're doing u substitution, okay, if you ever do u substitution, throw a du on the end of it. Always. Because that's taking your chain
So
rule
what you're
into
saying is
account.
when I get to the point where I'm gonna plug that thing in, I gotta stick it.
Yes.
Stick it in.
Just stick it, because it's the chain rule is what it's doing. If I put this in here, that would be your chain rule taking over right there. That's what you're doing, is you're doing the chain rule of that. It's just not in there right now.
I'll just think about whenever I plug it in.
Yeah. U substitution, put that du in there every time. Yes. Yes. Okay, shut up.
That's your sexual tendencies.
And I'm going to show you, I'm doing this because it's going to make my life just a little bit easier when I go to plug in. Here, this is u plus 1, and this is negative u plus 1. So the u's cancel, so I end up with 2 up top, right? Which is a lot easier than plugging in what I have for u each time. And then I have u plus 1 squared, and I still have the du. Y'all okay there? Where are you at? That's the 2 came from the 1 and the 1. No, you're not. You can do this. This is actually 4 times u minus 1 over. This one was tough. Now it looks a lot better to plug in than it did when it was here.
For every u, you're gonna plug in du, which is.
No, for every u, you're going to plug in 1 over x squared minus 1. For every du, so remember u is 1 over x squared minus 1, right?
Yeah.
And du is negative 2x to the
Well, you
negative.
can go ahead and plug the x into that.
So let's go ahead and plug it in. And then you could, once you get this in.
What's x? What's x again?
Yeah.
Why is it only
Wait.
two is all like from the past two on?
Well, because this is like multiplying fractions, so it's like 2 over 1.
Miss McGee, what's x again? Like what?
Negative 1.
Couldn't we just go ahead and plug x into? Plug that into.
You could. You certainly could. So you want to say, because I'm evaluating when x equals 1,
There's negative
so u of negative 1 would be, that might be easier if you do it like that. 1 over negative 1 squared, which would be 1 minus 1, which would be 0.
How do you know when the negative, like, I always get messed up on
If you're plugging it in and you're plugging in a negative number and then you're squaring it, it's going to be positive.
that. Think about it.
If you have something like this, that says square it first and then do the negative. So these are two different things.
All right, so it equals 0. So then that means we can just plug 0 in at all the u's.
Correct. And then,
And you know what the derivative is of 0? It's 3. So when you're not plugging, you can go ahead and use
You probably got
no one
confused.
would care.
You probably got confused.
No one would care. No one would care. Wow. Shut up. So you don't even know how to apply it.
so now I can just plug it in since I am evaluating it those. If that's easier for you, by all means do it that way. There's nothing wrong with that. Since I'm evaluating at a specific point. If I needed a general formula, of course, I'd need to plug in with these, but whichever.
Did you do a question for that? For the, when you're calling the derivative of, did you add negative 1?
I did power rule because this is x to the negative 2.
Oh, you're right. Yeah, okay.
So now I'm just going to plug in. So for every u, I'm plugging in 0, and for every du, I'm plugging in 2, since I'm evaluating at this specific point. So 4 times 0 minus 1 over 0 plus 1 cubed times du.
So, negative 4.
4 times negative 1 over 1 times 2.
The x is negative 1.
Is that the answer? Answer.
You don't get one.
Smart, Dylan, to recognize that there.
You don't get one.
Plug in. Helps. Okay,
Yeah.
good. Do it. Yeah.
Yeah. You gotta wait till you get to it. What? Yeah, for real though. I'm so serious.
Anything else from your homework?
I feel like I have a great understanding.
Let me give you one problem, see if you can do it, and then we'll take a brain break.
All right, let's do it. Let's do it, Mr. Lee.
Now, I know, that's why I want to give you one to do.
Except for math. Shut up. I'm tired of listening.
Find the derivative. This is still nothing like what you gave me yesterday.
do this? Oh, I found that on YouTube. Can you tell me what the derivative is? What's the derivative of music? I need to know that. I don't know the derivative.
So tangent.
Oh, we just did that, didn't
We did.
we? Yeah, you do.
You don't have to simplify it, just get it. We'll simplify it. Yeah, but I don't know what the answer
I
is.
don't understand why I'm so smart with this.
what did you get? Did you get 12?
I think the last problem is it should be like this. And then it should be like,
There wasn't a square.
our rules.
Good job.
Yes.
All right, we'll do it together. Make sure you have enough room.
Well, I think I got it.
Power rule first. 12 cosecant squared 1 minus 2t minus 5t squared.
Yeah.
Now derive cosecant.
Yes.
So that's negative cosecant.
That's not the inside. That's not the inside. Why would you?
Oh, you had to
No,
subtract
it
1
is.
for the power rule.
How would
Look, this on the outside of cosecant, the outside, then the cosecant.
How do you? I thought the things in the parentheses.
That's the next thing.
So when you have a
That's the
when you
next
have a trig function raised to a power, always do power rule first, then derive the trig function, and then do inside.
Okay, then we gotta get.
All right. No, you're not. Now chain rule for the inside, so times negative 2 minus 10t. I can.
So how are we supposed to, so how did we know that cosecant was the inside? I thought that the thing in the parentheses.
Well, that's the second inside. That the cosecant is the first inside thing.
For trig functions, always do power rule.
But if there was no
The
if
trig
there was
and
no
then
exponent
inside.
around the cosecant, then that would be your inside.
Oh, let's go.
So you're telling me we're doing the chain rule to the trig function?
Yes.
Yes. This is preposterous. It's repulsive. It's
blasphemy.
It's blasphemy. It's stomach.
It's heinous.
Stomach churning, vomit inducing.
All right, here's what I'm going to do, just so if you were in a multiple choice situation and needed to clean this up. I see this negative, I see this negative, and this negative. So I'm going to change this to, I'm going to kind of factor a negative out and make this 2 plus 10t. Right? And then I'm going to multiply these two things together. So 24 plus 120t. And now let's put, because all of our stuff is the same here, let's do...
Wait, what did you just do? What did you just do this for me with the 24?
Okay, so what I did, this I could rewrite as negative 1 times 2 plus 10t. I multiplied 12 times 2 plus 10t. Cosecants, I have 3 of them, all with the same thing that follows. So I'm going to say cosecant cubed. I feel like this is one of those problems that makes you look really smart when you work it, but there's not a whole lot of steps in it. It's just keeping up with the pieces here. Cotangent. Does that mean something stupid? Thank you.
I don't wonder why I do it. I do not wonder why.
That's the end. I don't see anything else I could do with that to manipulate. What's that?
That was good. That was pretty good. I mean,
Well, so I multiplied the negative 1 and this negative 1 to get positive 1.
see, you know, the thing is, like, on the AP exam, I totally could have gotten that, except for the fact that I don't know the trig.
This wasn't an identity, though. You don't know the trig derivatives.
Yes.
And I don't know if it would help you, but
I know
this
the
is
identity.
1 over sine cubed. This one would be cosine over sine. So no, that wouldn't really help you cancel anything out either. So I'd probably leave it like that. Let's take a break. Come back together.
Well, no, I actually take her to the Lincoln Street preschool.
Yeah. want you to find dy dt.
Well,
There's no t in there, right?
Oh, I know if you would just put DC in your answer, right?
You're actually really close. You're really close.
You didn't write down the extra. You have to change.
I didn't what?
You didn't write down.
Right. Yes. I didn't do what?
So it's saying that you that
Yes, but I wanted you to find the derivative first without.
No. Well, there's still count.
I got my answer.
How you don't?
Okay,
I know I'm right. Yeah, he's not right. He's nuts. Huh? Wait. So do you plug 1/3 or 1?
So here's what I'm going to do. To find dy dt,
Yeah.
I'm going to do. Huh? No, what I'm going to do is I'm going to do the derivative of this, but then I'm going to, instead of following it with dx afterwards and it just being 1, I'm going to follow it with dx dt because I want the derivative of x with respect to t.
So everywhere you take the derivative, you just stick that in there?
Do what? Well, what did I tell you? And then I told you to evaluate it when x equals 1 and when dx dt equals 1/3.
Well, it does already though, because X already does. X already equals 1.
So you just plug them in, exactly. All I'm doing is I'm still doing a normal derivative, but I'm following it and I'm saying, I'm kind of chain ruling it essentially is what I'm doing, is I'm taking the derivative of x and then I'm saying, okay, but since I'm not finding dy dx, I'm finding dy dt. So I need to take the derivative of x with respect to t every time I do something here derivative-wise. So you get 2 times 1 times 1/3 plus 7. This is really setting you up for implicit differentiation tomorrow is what this is doing. Yeah. 2/3.
I do not want to hear that.
It's not bad.
Implicit differentiation.
Bless you.
Yeah, if you can't even pronounce it, because you know.
So it's 3.
Why would it not be explicit?
You know what else is implicit?
You know what else is an opinion that it's right to date someone is 2 years younger.
Can you at least pronounce it? Can you even enunciate that word?
What, no? I was.
I just don't like people with the last name Boyd.
I know, like, people with the last name Shelter.
Find the lines that are tangent and normal to the curve at the point x equals 1.
AKA. First again? Tangent minus the derivative, we know that. Normal.
Okay.
A rock.
That's it?
normal is the opposite.
Right. So the first thing I need is the derivative. I need the derivative when x equals 1. Do you agree with that?
Yeah. You gotta get the derivative.
So,
Then plug in 1.
what do I do here?
Well,
Get it in.
you do power rule first. Correct?
No, you don't
gotta
get
go
a power.
I don't have a power rule,
But
right?
you have coefficient then.
Secant squared. So it's 2 secant squared.
Hold up. What about the 2?
You can whip it out.
I'm confused.
No, actually.
Okay, where are you confused?
Like, how does that 2 not at least turn into 0?
Because you pull it out and pull it.
Right, it's kind of like if you have 2x to the fifth.
Then,
Right.
but like that would, oh wait, see, it technically is probably just one.
Just 1 times 2 to,
That's what I
to
was
the
saying.
0. So yeah, technically it is.
Okay.
All the rules still work.
I'm gonna
It's
be
just
honest
we
with you, if I went to living that, I would.
don't get rid of the 2 van.
Thank you, but just do power rules.
So and Dylan's right. I mean, the power rule still works. You could do 1 times 2, so that'd be 2 times. What happens is this becomes a 0, and anything to the 0 power is what? 1. And then you would do derivative. Remember, we do, when we're talking about trig functions, we do power, trig, and then inside. So that was power. So the trig would be the derivative of tan is secant squared of blah times, and then you do the derivative of the blah, which is what we have down here.
All right, now.
But the 2 is still there.
Now we can plug in X.
Okay, so now we can plug in x. So we end up with, and I'm going to make this pi over 2.
Yes. Just like 2 over 1 times power.
Right? Oh, what?
So you just do
So,
that.
so secant squared, it.
Wait, you multiply.
Right.
Pi over, so you multiply square root of 2 by itself, right?
You would square, well, you got to flip it first. So at pi over 4, it's square root of 2 over 2. But because this is,
Yeah, that'd be 1 over,
it's going to flip,
cosine.
right? So
1
it's
over
going to
cosine.
be 2 over square root of 2
And then so it's.
squared.
Huh? What'd you?
The answer is
Because it's secant. Secant is 1 over cosine.
Okay, so that was
So the answer is
So I got pi over 2, yep, 2 over square root of 2 squared. Don't get lost in the unit circle stuff.
it's just 2. Well,
So,
square root of 2.
so, right, that's 4 over 2, which is 2.
But, hold on, how's that 4 over 2? Okay, the square root.
Yes, Van, I multiplied these two together, and that's what gave me this one. That's because when I plugged in 1 here, pi times, yeah. Which 2? The second 2. 2 squared is 4, and square root of 2 squared is 2. So 4 over 2 is 2. Y'all see you're definitely getting caught up in the numeric part of it and not the calculus part of it. Yes, so secant squared is 1 over cosine squared. So what I did was I found the cosine of pi over 4, which is square root of 2. So because it's 1 over, I flipped it, and it became 2 over square root of 2.
You can just flip it like that?
That's the slope of the tan line.
Oh, well, you multiply by the reciprocal.
So the slope of the tan line is pi. The slope of the normal
Would be negative. Yes.
But I need a point and a slope to write the equation of the line. So, right, I have to go back up to the original equation and put the 1 in. So y of 1 would be
Well, it would be.
2 tan pi over 4. What's tangent of pi over 4? That's easy.
Well, that's square root of
1. Because they're the same. Tangent is sine over cosine. And if
Oh,
both coordinates are the same, so 2.
Well, where'd you get the 1 from? Where'd you get the 1? Oh, wait, did you just plug in 1, I guess, because?
Because it told me 1. It said when x equals 1.
Oh.
Alright.
So then normal would be y minus 2 equals negative 1 over pi. So your homework's going to get a little bit hairier than that. Number 65 asks you for orthogonal curves. Man.
Yeah, we're not doing. No, we are doing 69. We're doing 67 through 73.
It was supposed to be on there. 65 is supposed to be on there. That's okay then. It's not. Okay, that's okay.
We already have a lot of problems.
You have a particle motion. 69 is a particle motion. 70 is an acceleration. 71, Polyman part. Yeah, you have several particle motions. We have 8 minutes. Let's work through number 73 together because generally the last one's the hardest. We don't even use numbers half the time in here now.
You probably still didn't know what your multiplication Wait, is it 40?
All right, so this says for oscillations of small amplitude, we may safely model the relationship between the period t and the length L of a simple pendulum with the equation blah, where g is a constant of acceleration of gravity at the pendulum's location. So that's key. Remember, g is a constant. If we measure g in centimeters per second squared, we measure L in centimeters and t in seconds. If the pendulum is made of metal, its length will vary with temperature, either increasing or decreasing at a rate that is roughly proportional to L. In symbols, with U being temperature and K the proportionality constant, dL du, this is typical on like an FRQ type question where they will give you all this background and all this stuff, but then they'll just spell the equation out for you. And that's what you're using to do our homework. This is all being given. Okay.
Oh, wait, I've never had to get that equation.
They gave it to you. All this. I'm still reading the problem. Assuming this to be the case, show that the rate at which the period changes with respect to temperature. Remember what did it say period was? T. So we want the rate of change of T. Show that the rate at which the period changes with respect to temperature is KT over 2. And U is the temperature. Any ideas what we're going to do?
Are we gonna do the same thing like we did for, 56?
We're gonna find the derivative of that equation.
Kind of, yes. Yes, it is going to be very similar. This is a constant. So we have two variables. The derivative of that would be 0, right? So here's what I'm going to do. I'm going to take, remember, I'm talking about in terms of temperature. So I'm going to take the derivative of T with respect to the temperature. So yes, just like we did the other one.
How do you know where it's from?
Well, it asked me for the rate of change of T, so I know that's a dt situation. And then it said with respect to temperature U, so dt du. And they told me, this was the key, this is what clued me in with respect to U, is because they gave me dl du. Well, because what I'm thinking is whenever I take this derivative, this is the only other variable in this problem, and I need to take it with respect to U.
What's the KT?
That's what they're telling you. They're saying, show that this is the derivative.
Oh.
So let's find the derivative here. So I'm going to do the whole derivative here, and then at the end I'm going to throw the dl du on there, right? Because I want it with respect to U. This is really the same thing as 1/2. And I could actually rewrite this 2 pi times 1 over GL to the 1/2. Would that make sense? G is a constant. G is a constant and it's not a variable. So if it's a constant, let's say it's 5, then that would be like saying 1/5 times L. Instead of doing L divided by 5 and starting to think about, oh my gosh, do I have to do quotient? Do I have to? I'm going to just write it as this multiplied so I can think about a power rule situation because it's a little easier.
Would it not be
Think about
easy?
that. Either way, doesn't matter. All right, so say again. Okay, so right, pi times to the negative 1/2, right?
Then you gotta do the inside.
Wait, I thought, what, 1/2 minus 1 is
Negative 1/2. Negative 1/2 minus 1 is negative 3/2. But positive 1/2 minus 1.
And then you gotta do,
If I have a half, but then I take a whole away, I still owe a half.
okay, so see, why I would say leave it in there as a fraction. You gotta do quotient.
You don't have to do quotient rule there because G is a constant. It's not a. So if that was just 1/5 there, what would the derivative be? 1/5. So I'm going to do 1 over G. But remember, because I'm with respect to U, I need to throw a dl du in here.
Wait, why did you do?
That's the constant. Remember, this is a constant.
Ah!
Where'd it go? Where'd it go? Say again. I know. L is a variable. Yes. All right, let me try to get through the rest of this quickly. So this one's tough. This one's tough. All right. I'm gonna plug in what I was given. I was given dl du, so I'm gonna put a kl there. Right. So I end up with pi times. Now, if this is L over G to the negative 1/2, it's really G over L to the positive 1/2.
That's an L comment?
Yep.
You would flip it, man. You would flip both of them. So G goes to the top and L goes to the bottom.
That's not.
That's an L.
That's an L. Not kidding. Ways. All right, I got that.
It looks like going.
Now, how do you know what to do with K?
All right, listen, the bell's fixing to catch us. Here's what I want you to think about. Look at what you have here, right? KT. T is all of this.
You can just finish it right now. I'll be late. I want to see.
Okay. T, remember, I'm showing that this is the case. T is 2 pi times the square root of L over G over 2. So that's what I need this to look like. So my goal is to manipulate this purple one to look like this purple one. If I can make that happen, then I've proved it. What do you see that I could do?
Well, you can leave the 2 on the bottom. The G needs to go back up top.
The G needs to go back up top.
Well, the whole thing does. Everything needs to be above that too, so I'm not sure.
You can move the K around.
The K's there, that's for sure.
I don't know. I really don't.
Can you flip that G into?
Well, you could, but you need a 2 on the bottom still.
You do.
Wait, do you know how to do this? Or are you thinking?
I'm thinking about it. I mean, I've done it before.
So what you're saying is you need to turn that, make the T the same.
Right.
No.
The K and the 2's already there.
No, you know what though? You know what, G, that G would have to be on the bottom though, so you would have to make that negative.
Well, but so if this is G to the 1/2 and you've got a 2G on the bottom, that would leave me with,
Oh, that's right.
right?
Yeah.
Well, now I see my square root of G coming out.
Well, what about the 2?
What about the 2? Let's see. Well, these 2's technically cancel out, right?
Yeah.
So this is k times the square root of 2 over g. There's a pi in there. We're almost there. Adam. See why my day just goes downhill.
Like, how you do the scale and then the pile on the outside, so you do it together.
I'll finish working it for you and I'll see.